All right, welcome everyone. Today we're going to tackle a classic problem, number 1.49, from a book that has probably given a workout to every serious physics student out there, the one and only Irodov's Problems in General Physics. So if you're ready for a really satisfying deep dive into rotational motion, you've come to the right place. You know, Irodov himself tells us in the preface that these problems are meant for an advanced course. And that's the key right there. They're not just about finding a formula and plugging in numbers. No, they're designed to make you think, to really build an intuition for the physics. So let's not think of this as just a problem, but as a great workout for our physics brains. So here's the game plan for today. First, we'll lay out the challenge itself. Then, we'll spend a moment decoding the problem, getting our tools in order. After that, the fun begins. We'll solve for the angle, then we'll find the velocity, and to wrap it all up, we'll step back and really visualize what this motion looks like in the real world.
Okay, let's get right into it. Let's take a look at the problem we're solving today, problem 1.49.
So we've got this solid body rotating around a fixed axis. Simple enough, right? But here's the catch. Its angular velocity, omega, isn't constant. It actually changes depending on how far the object is rotated. The problem gives us this relationship. Omega equals some initial velocity, omega naught, minus a constant a times the angle phi. We also know it starts from rest, so at time 0, the angle is 0. Our job is to untangle this whole thing and find expressions for both the angle and the velocity that depend only on time.
Now, before we start crunching numbers and doing calculus, it's super important to just pause. The first step in any physics problem is to figure out what's really going on and what principles apply. So let's get our toolkit ready.
And you know, the absolute most important tool in our entire kit is the definition of angular velocity itself. Omega is simply the rate of change of the angle phi with respect to time. It's d phi by dt. This little equation is the master key. It's the bridge that connects the information we're given, which involves the angle, to what we want to find, which is everything in terms of time.
Okay, let's lay this all out nice and clear. On the left, we have everything we know, the equation connecting omega and phi, and the fact that we start at angle 0 at time 0. And on the right, that's our goal. Find the angle as a function of time and find the velocity as a function of time. Having it laid out like this gives us a crystal clear plan. All right, we're all set up. Time to make our first big breakthrough. We're going to dive in and figure out the expression for the angle phi as a function of time. Let's do this. And you know what? The first step is actually pretty straightforward. We have two expressions for omega, right? The one the problem gave us and the fundamental definition. Since they're both equal to omega, they must be equal to each other. By setting d phi by dt equal to omega naught minus a phi, we've just created something called a differential equation, and that is the beast we need to solve. Now, to solve this, we use a really powerful technique called separation of variables. It sounds fancy, but all we're doing is a little bit of algebraic housekeeping. We want to get all the terms involving our angle phi over to the left side, and all the terms involving time, t, over to the right. It's kind of like sorting your ingredients before you start cooking. Okay, next up, integration. And it's so important to remember what this actually means in physics. We're not just doing a math procedure. We're literally summing up an infinite number of tiny little changes. On the left, we're adding up every tiny step in angle, and on the right, we're adding up every tiny tick of the clock that goes with it, all the way from the start of the motion at t equals 0. So once we do the integral, we get this expression with natural logs. But this is like a general solution. It could describe a bunch of different motions. We need to find the one specific solution that matches our problem. And we do that by plugging in what we know, that at time 0, the angle was 0. This is what nails down the exact answer for us. We are so close now, just a little bit of algebra to clean things up. The first move is to use the properties of logarithms to combine those two terms on the left. Then comes the magic step. We exponentiate both sides. What that does is it cancels out the natural log and it finally frees up our variable, phi, so we can solve for it. And boom, there it is. After just a little bit of rearranging, we got our first major result. The angle phi as a function of time is equal to this constant omega naught over a multiplied by 1 minus this exponential decay term. Fantastic. One down, one to go. So now that we have this awesome expression for the angle, we can use it as a tool to find the second piece of the puzzle, the angular velocity omega as a function of time. And this is where things get really cool. In physics, it's always a good sign when you can get to the same answer in more than one way. We have two options here. Method 1 is pure algebra. Just take our shiny new equation for phi and plug it right back into the original equation from the problem. Method 2 is pure calculus. We just remember our definition that omega is the time derivative of phi.
And look at that. It doesn't matter which path you take, algebra or calculus, they both lead to the exact same beautiful, simple result. The angular velocity is just the initial velocity times an exponential decay term. Getting the same answer from two totally different methods gives us huge confidence that our solution is solid.
Okay, we've got our equations. We've solved the problem, right? Well, kinda. In physics, getting the answer is only half the battle. The real fun and the real insight comes from figuring out what these equations are actually telling us about the motion. Let's bring this math to life.
This little table really tells the whole story of the object's life. Let's check the start and the finish line. At time t equals 0, if you plug that into our equations, they give us exactly what we started with. Angle is 0 and the velocity is at its maximum, omega naught. Perfect. Now, what happens if we let time run on forever? As t gets huge, that little e of the minus at term goes to 0. This means the velocity fades away to nothing, and the angle sneaks up on a final, maximum value of omega naught over a.
So, let's put it all together. What does this motion actually look like? The object kicks off rotating at its fastest speed. As it turns, it immediately starts to slow down. But it's an exponential slowdown. It decelerates really quickly at first, and then that deceleration eases off. Importantly, the velocity gets closer and closer to 0, but it never goes negative, so the object never, ever reverses direction. It just gracefully glides to a stop at its final resting angle.
And that leaves us with one last really important question for you to think about. We just analyzed a motion where the deceleration changes. So how is this motion different from the stuff you usually see in textbooks, where deceleration is just a constant number? What would the graphs of angle and velocity look like for that simpler case, and how would they compare to this one? Chewing on that question is the absolute best way to make sure you've really grasped what makes this Irodov problem so interesting. Thanks for joining me for this breakdown.